Hi, welcome back. So I've just written down everything we found in the last few videos, everything we drew a box around. So all of our first order conditions are simplified first order conditions. All of our budget constraints or all of our constraints in our optimization problems, and all of the laws of motion. And also I wrote down our competition condition. And this is our solved system. And you should see that we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 equations for 10 variables. The variables are CT, LT, WT, PT, RT, IT, YT, KT, what else? AT, what do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, and MCT. Okay, 10 variables, 10 equations. A couple notes. First, note that I just wrote down the T's. Okay, so in terms of relationships, what do we need to define? We don't need an equation for KT and for KT minus 1. These equations are true for all time. So if we have an equation for KT, we have an equation for KT minus 1. And the same thing is true for these expectations. The expected value at time t of RT plus 1, if we have an equation somewhere in here that pins that down, and we do, it's this one. This pins down, whoops, what did I do wrong? The Euler equation is going to pin down the rate of return of capital here. We don't need one for RT plus 1 as well. Okay, so what do? You're going to go through the equations. You're going to solve the first order conditions. You're going to simplify the first order conditions so that you can get equations like this. You get the labor supply. Okay, you get the Euler equation. Okay, you get the demand for capital, and you get the demand for labor, and you get the marginal cost. You go back, you add to that all of the restrictions on the model, the budget constraint, you add in the production function, and then you add in the laws of motion. The law of motion of capital, the law of motion of technology, and then we get this funny little condition at the end, which is our competition condition. And you're done. I mean, this is the solution to a real business cycle model. So I just really wanted you to get your head around that idea that you're not looking to box in one thing, but instead you're looking for a system of equations that's going to pin down all of the variables at any given time. And that's exactly what this system does. If we were able to solve this, if we were able to put these together and solve for the state variables as a function of parameters only, then we would be done. We would be able to iterate this forward with that that general formula from these 10 equations. In theory, we could come up with an equation xt plus 1 is equal to g of xt minus 1, xt, expectation of xt plus 1, and et. Okay, so it's a multivariable equation. We somehow combine and stack all of these things, and we get one function g that's going to take us through all time. Now, it turns out you can't do that in this case because of the nonlinearities involved. So here, maybe pause the video and have a think about what are the actual state variables in all of these equations. So what you're going to do is you're going to look through these, and you're going to look for all the variables that occur with a t and a t minus 1, or a t and a t plus 1. Okay, so pause, have a look, and write it down so you have to commit to it. Okay, what are all the variables that occur with a t and a t minus 1, or a t and a t plus 1 at the same time, because those are the states. Okay, and if you come back, you looked around and you found, okay, so maybe you found this ct plus 1. Okay, you found this ct plus 1, you found this rt plus 1, you found this pt plus 1. Okay, you definitely found this kt and this kt minus 1. That looks good. And you definitely found this AT and this AT minus 1. That looks good. So the question is just, is this CT plus 1 a state variable? Is this really a future value of CT? And the answer is no, it's not, because it's actually an expectation of CT plus 1 at time t. So this isn't really an update rule. This doesn't describe how CT moves through time. This describes how people's beliefs about CT plus 1, or it describes what their beliefs are at time t. Okay, so there's a distinction there. This equation really tells us what will the capital stock be tomorrow. This equation only tells us what do people believe that their consumption will be tomorrow. So we can't solve this equation for CT plus 1 on the left and put CT plus 1 on CT on the right and then say that this is the update rule for CT. It doesn't work. So CT is not a state variable. Neither is RT plus 1, neither is PT plus 1. There's only two states, KT. The states are KT and AT. So in principle, you would like to reduce all of these equations to be only in terms of KT minus 1. What you would want to do is substitute all of these into each other and slowly grind the problem down so that all you have is some function. You want some function such that you have KT equals a function of KT minus 1, AT minus 1, epsilon t, and all the parameter vectors. So theta, big theta will just be all the parameters. This is what you want, but you can't have it. Maybe it's interesting to try once to see how far you can get, but you can't do it because of the nonlinearities involved. So instead, we have to do a linear approximation. And to do that, we need to have a point that we're going to approximate around. We need a special point where our model's dynamics are constant. And then we can think about deviations from that point and how it moves away and comes back. And the answer for the special point, of course, is the steady state. So in cases where you cannot have this, there are simpler models where you can have this. And maybe we'll look at one of those in this video series because it's interesting. But for this model, for this basic RBC, you can't have this. So we need to do a linear approximation. And so we need to choose a point to do the approximation around. And that point we're going to choose is the steady state. So in the next video, we're going to begin solving for the steady state. So have a try by yourself. Remember, the rule for the steady state is just that all the variables xt go to xss. Okay, x steady state. And they all go together, right? So for this equation, okay, for this equation, you write CSS, you also write LSS, you also write WSS, you also write PSS. Okay, you can't just do one and not the others. Everybody goes together. Everybody goes together. Remember, the steady state is a feature of the system and not of the variables. Okay, so send everybody to the steady state and then set all the shocks ET to 0 because nothing bothers you in your happy place. So change all of these to steady state, see if there's any obvious simplifications, and then come back and we'll do it together. And I'll see you there.